about the big three conservation laws. I alluded to this earlier, but let's go ahead and look at it again. So I was working on this chapter today, and I want to point out something. You may notice something subtly different. Look at your 11.18 in the book. I finally got around to notice I changed length L to length D in my version. And I did that in the solutions as well. And I did that so that I don't have L and L in the problems. So in the solutions, just be aware, you might put a note in your workbook for pages 93 through 97. L, the length of the rods are always going to be D. All right. So just so that's in the chat. Come on, chat. Where are you, chat? Chat. All right, it's lost somewhere. All right, whatever. Okay, but so, all right, physics love conservation laws. Why? If you know which conservation law to write down, that allows you to get an equation relating a before and after picture and solve for something. Properly identifying this law, which one you could use, is crucial. I don't normally just read what's in the book. That tells you how important this is. Many physicists say this is the biggest takeaway from the course, understanding these laws and how to apply them. Okay, the point of these questions is to figure out when to use them more than the technical details. So if you find yourself on any of the problems on pages 93 to 97 getting lost in the technical details, remember the most important part, whoops, oh, there's a typo there too. Looks like I introduced one. Whatever. That's supposed to say the second two laws, but yeah, all right, page whatever, 93 typo. Gosh, whatever. Adding typos to the book, great. All right, so just to give you an idea here, we talked about this before, but I want you to do these at home. So I want you to think, if you have this situation on test day, which conservation laws apply? Okay, and then is it rotating or translating? Why do you need to do this? Because on test day, you're not going to have a lot of time to think, what should I do for this problem? So, and then where is it going to rotate, etc. And then here's one that has a pivot. Okay, which conservation laws apply? And so, all right, great. And so now here's another one. So notice there's not a lot of math here. It's maybe draw the picture and think, is it doing, what is it doing? So 11.20, same one here. So you might notice on 11.21, everybody go to page 94, 11.21. Notice that I labeled the speeds are the same there. That was another Alexis comment. He found out that I didn't specifically state that, which is good. So you might just throw in there that they're moving at the same speed on that one. I drew it that way, but I didn't explicitly say it. And again, like I said, I'm changing everything to D, right? Just because it's an angular momentum chapter. You can go through all of these and see what happens when it hits at the center, at the end, with a pivot, without a pivot. What if the rod is moving? What would happen? Here's another one. Here's a variation, figure skater. Here's a planet. Here's this one. And so we've seen a lot of these problems, but the idea is you can kind of go through them and see what you should do, what you shouldn't do. And then afterwards, I made a bunch of notes here. So go through those problems and do it. Here's another problem you might try, and you can see, can you do angular momentum on this? And I'll let you find out. Here's another problem, another problem. And then out of all of these, this one, 11.32, make sure you put a star next to it and do it all the way through. So 11.32, actually do this problem. Actually do problem 11.32. It's messier, but there's something in here that I discovered after I assigned it. There's a bunch of students that were like, what? And so just, yeah, try to set that one up. That way, when you read the solution, you'll get something out of it. Put a star next to 11.32 and make sure you do it for real. Okay, all the rest of the ones, and that's it for chapter 11. So if you're a CS major and you're looking for something to do, Well, here you go. You could code this experiment and you could allow the user to select the masses and impact locations, and you could have it compute the center of mass, do angular momentum, and you could update the position using this. You could do this, et cetera, et cetera. And so you could, in theory, make an animation of that. It should be really easy. All right. Have fun. Okay, so I'm confident I could do it. So hopefully those CS majors out there could do that. And if that interests you and you really want to try that one, maybe we could work out an arrangement tomorrow in lab if you want to do that in lieu of maybe one of the lab activities. And maybe that would be the week 17 or something. All right, so that's it. Chapter 11 is done. All right. Okay, so Nick, go ahead and cancel that time, and maybe Nate Dogg. Well, let's talk about that tomorrow in lab. All right, so we could discuss it at length in lab. I do want to get through some stuff in our last 40 minutes here. So yeah, Nick, that's cool. Okay, thanks, Nick. And then all right, cool. Check your email for that. All right, we are doing chapter 12, but we're going to skip over it and go to chapter 13. All right, so. I'm going to go ahead and talk about a couple of things in chapter 13, and I'll probably call off class early and just be here for homework questions if you have them. All right. So let's go to page 117. I'm not sure, Jay. We can talk about it in lab tomorrow at length or after I finish. Okay, Jay. So we'll get your question for sure before I leave today. But let's look at page 117. All right. For now, let's get to that. All right, so page 117. And I'll go ahead and share the screen as well, so we're all talking about the same thing. Oh, whoops. Oh man, I was right there before. All right. Okay. This is an important topic, especially. I mean, I'll be honest with you. I could care less about astronomy. That's just not my thing. You know, I like looking at the stars. I like seeing it when Vince puts out a telescope, but it's not something I'm extremely passionate about. However, the mathematics involved in this chapter is very similar to the mathematics of Physics 163. So if you do a good job on this chapter, you're setting yourself up for success in the hardest class you may ever take. If you do a bad job in chapter 13, you're just going to have to do it more than once and suck at it more than once. So you better do a good job on chapter 13, do all the practice, and do a good job at it so that Physics 163 is a lot less painful. By the way, all that stuff in chapter 9, all that stuff with integration and center of mass also relates to Physics 163. So all this stuff, I teach Physics 161 from the standpoint of preparing you to pass 163. Most students say it's one of the hardest 3 classes they ever take, all right? Let's check the chat and see if there's any questions there. Oh, come on. Why is my chat not popping up? Oh, there it goes. Okay. Yeah, we're skipping chapter 12. No. Yes, okay. Yes, got it. All right. Okay, let's get back to it. Thanks for helping out, everybody. All right. So you got to get used to these terms. And notice this little sucker right here. In chapter 3, I was really ruthless about making sure you understood unit vectors. It's because we need it in both coding and in universal gravitation and in Physics 163 all the time. So be clear. Different books may say things different ways. What do these things mean? This is a vector. Look at that. It's not a hat. It's a vector. Look at that right there. It is not a hat. It's a vector. Okay, and it's going from 1 to 2. And it's going center to center. So R12 is the distance, R12 is the vector, R12 hat is the ratio. That's the direction. So notice this is the direction from 1 to 2. And look at this carefully now. The force that 1 exerts on 2 is directed towards 1. Think about this. When you have two objects, gravity pulls them together towards each other, inwards, negative R hat. So this is getting sloppy. Let me clear this out. 1 on 2, right? This makes sense. We expect it to point this way, right? We expect it to point. 1 will pull 2 towards it using gravity. So notice if I go from 1 to 2 this way, that's not the right direction. That's why I have negative 1 to 2 hat. That's enough on that. Good. And then it's going from the center to center. I just want to point that out as well. Center to center distance. So that would be like sphere 1 pos. In Python, right? So that's a way you could get that. We're going to use that in coding. That's a way you could get the vector between these two, all right? And then if you wanted to do hat, you could literally just write hat and put parens around that, and you would get the hat vector between them. That's cool. Now look carefully here. This is the magnitude, okay? So a lot of times what we'll do is we'll say force equals G little m for the satellite or some small mass, big M for a planet, and then we'll say over R squared, where R squared, R is the distance between them. That's another way that you often see this written, okay? They're the same way. And just remember, if you're worried about screwing this up, you can always write down the vector using I hats and J hats and verify that the force points the right way. And I will help you with that. Okay, that's the force, gravitational force. If I want, I could use the equations on the equation sheet. We can get gravitational potential energy. If you recall, let's see where that is here. It's something like this. Delta U equals minus the integral of force dot ds. And so from that, just look, you get a minus sign, you get an integral, blah, 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 blah. You do the math, we get this. Okay. So we're going to focus more on using this than deriving that. And I want to point out, this is probably worth summarizing right here. So let's make sure we read this again, page 117. This is something that may come in handy in chapter 11 when you're reading it. The potential energy equation is technically associated with a pair of masses. So two masses share potential energy inside their gravitational fields. Why does this show up in chapter 11? I just want to point this out. Whoops, let me do, let's say you had the Earth here. All right, there's the Earth, and you put a block here. It turns out it's not technically, so when you've been doing problems up to now, we used to say, let me get my drawing tool here. We used to say that GPE, gravitational potential energy, was equal to mgh, right? However, when we're doing astronomical bodies, we now want to use this equation. This is valid for these planets with satellites and things like this. So if you have a planet and a satellite, don't use this one anymore. And I will explain in a problem how these two are actually the same equation. You might not believe it, but I'll tell you in a minute about that. So this equation talks about the potential energy. And notice it's negative. That is correct. Now, check this out. Think carefully. If radius gets bigger, if radius goes up, you get a smaller negative number. That's the same thing as going up in potential energy, right? I'm going to say that again because Lag City, you know. Again, if you put in a bigger radius, this number gets smaller and you have a smaller negative number. That's the same thing as gravity or gravitational potential energy becoming more positive when you go up. So in that sense, it's exactly the same. All right. Potential energy is always negative. And then watch out. Energy uses the radius, force uses the radius squared. And again, potential energy is a scalar. Now I'm going to stop and get that chat question here. G is some constant. It's 6.67 E negative 11. And then the units, you could figure it out from the force constant. So notice there's little g. So you may hear me say this. Little g is our 9.8 number. Big G is 6.67 E negative 11. All right. So by that, I mean 6.67 times 10 to the negative 11th. So be aware. Whoops, let me share my screen. So this is not little g. G is a number. I think I wrote it up here right there. Okay. So that's the units. All right. Any questions about that? I'll assume it's good. All right. So let's start simple. Okay. Now, I know you guys are actually pretty intelligent. You're not dumb. But if you don't practice, you're about worthless, right? You know that you can't do anything useful unless you practice it. So let's take the time to actually punch in these numbers, right? If you're one of those students, it's like, oh, of course I can punch it in on test day. I know you can, but you'll be a lot better at punching it in and you'll have more time to check your work if you punch it in now. So look at all this scientific notation. It's been a while since we've had to deal with scientific notation. Maybe you're wondering why I spent so much time on it in chapter 1 and we haven't used it. This is when we use it. Okay. So now see if you can punch in the numbers and do this one. All right. And I'm going to go ahead and walk you through this. We'll use this as a worked example. We've got the Earth's mass and we've got the radius of the Earth, the sun's mass and radius of the sun, moon, etc. And then notice this final one. So to be clear, I also gave you not only the radius of these spheres, I also gave you the distances between them. And I want to point something out here. The center to center distance from Earth to sun. That is basically 10 to the 11th. Now notice the radius of the Earth itself is 10 to the 6th. I want approximately, 10 to the 6th. You could say it's 10 to the 7th. Does the radius of the Earth matter compared to this distance? Think to yourself, and then I'll tell you. Does the Earth's radius matter compared to the Earth-Sun distance? The answer is not at all. Okay, look at the Earth. Look at the Sun's radius. The Sun's radius is 10 to the 8th. Ish. Okay. That doesn't matter either. This is like at least 2 orders of magnitude larger. somewhere between 2 and 3 orders of magnitude. So we can ignore the size of these things if you really want. You can think of the sun as a point particle. You can think of the Earth and the moon as point particles for this problem. Obviously, don't consider the Earth a point particle if you're walking anywhere on the Earth. But when you're doing astronomical problems, the sizes and the distance between things are crazy large. Okay. Now, notice it's a bit debatable here. The distance between the Earth and the moon, that's 10 to the 8th. And so it's still negligible because it's about 100 times smaller. So it's about 1%. But there you could argue maybe the radius might matter a little bit. And if you talk about the tides, it definitely does matter, which we'll get to later. Okay. All right. So that's kind of walking you through this setup. Let's go do the problem and see if there's anything. Hopefully you've been working on it while I'm babbling here. Let's go look at the solution. Oh, I just wrote the number. That's a great solution. Usually I do this one on the board with the class. So to be clear, the force, I think we're doing forces, right? Force would be big G, mass of the sun, mass of the Earth, and then you got to make sure you put in the right radius. Radius, Earth, Sun. Don't forget it's squared. So hopefully you got this number and it wasn't a big deal. For the moon on the Earth, it would be force G, mass of the Earth, mass of the moon. Obviously, it doesn't matter the order you do them in. All over radius, Earth, moon. And I just want to point out, if you do the math, look at these exponents here, people. This is slightly interesting. Which object exerts more gravitational force on the Earth, the moon or the sun? Hopefully you look at the numbers and say, the sun exerts more gravitational force than does the moon. Here's a fun follow-up. Which one has a larger effect on the tides? What do you think? Which thing, the sun or the moon, is going to have a larger effect on the tides? Oh, okay. So a rounding error on part A. That's cool. I don't care about that. I'll double check it. So I'll check a rounding error on part A, 13.1 rounding error. I may have used a different mass or something for the Earth when I did it. Or maybe I just rounded up. Yeah. So yeah, here's what's baffling. Maybe you know the moon exerts a much larger effect on the tides, and yet the force is 100 times smaller, 200 times smaller almost, right? Look at those numbers. Why is it that the moon, which exerts 200 times less force, has maybe a tenfold effect on the tides? If only there was a problem in chapter 13 that discussed this. I guess we'll never know. Let's call that foreshadowing. All right. So we'll discuss that at the end. All right. Part C, potential energy. That's just U. Don't forget it's negative. So that was one of the things. And then it's G M over R, not R squared. All right. So hopefully you got all those numbers. And that's the same math for both of those. So that gets you this. All right. Punching in and double check with your calculator. You've got the solutions up on your machine as well, probably. So you can go around wherever you want. let's go back and look at this. Okay, and so this is a good question. I want you to look at parts C, D, and E really quick. This is important. All right. So we found the potential energy with the Earth and the Sun. We found the potential energy with the Earth and the Moon, but it does not get the total gravitational potential energy. What did we forget? Hopefully you saw Sun, Moon. So Sun, Moon, there's a way I like to write this, and let's see if I actually have that here. Let's go back to here. Whoops, wrong one. This, you'll see me write this a lot. The total potential energy of a 3-mass system, you have to add all pairs. All pairs. So there's the Sun-Moon pair also matters. And so there's the total energy. Now look at this. It's not a big change, but we do see the Sun-Moon pair matters a little bit. Actually, it matters more than the Earth-Moon pair, right? And so because the sun is so massive, it's going to dominate everything. But we do see a tiny change here in the sig figs, all right? So, all right, good enough. And then here's the question about the tides. All right, so it's about 180 times less force. But this, if you plot the field, whoops. Let's say we have radius, and let's say we have the force. Well, it's something that looks like a 1/r² law, which this is a very big deal. So it may seem like I'm just on a tangent here. So this is not alpha. This is called is proportional to. It looks like alpha, but it's is proportional to 1/r². And notice the force changes dramatically for small radius, and it doesn't change dramatically for large radius. And because the moon is closer, its gravitational force changes more. And so it's not that it has more gravitational force, it's that the sun is so far away, right? The sun's force starts way over here. And it's much bigger, but it's much flatter. So the sun exerts almost the same amount of gravitational force on either side of the planet. But the moon, because it's so much closer, experiences a dramatic change in gravitational force from one side of the planet to the other. So that's what I'm trying to say right there. And that's why the moon is the dominant influence on the tides. I'm going to stop that for a second and see if there's any questions here. Any questions on that? Looking good. Hopefully you're doing okay on those problems. Let's go ahead and look at the next one, 13.2. Yes. So let's look at 13.2. All right. Anybody know when the next eclipse is? April 2024. Go to Mazatlan. Okay. Actually, there's others before then, but that's the next one that's easy for us. April 2024, Mazatlan. I'll see you there. All right. Or you can go to Texas. But the cloud cover is about 30%. Not that I'm planning it. All right. Whatever. Let's get to work. Okay. Here's something useful to know. Let me get this out of the way. All right. What does this do on here? All right. Altitude. So I want to introduce a new term, altitude, and just beware. So altitude is right here. Whoops. There we go. Altitude is this distance. So we use this all the time. Planes are given an altitude. It's because it's so common to use altitude. it turns out, think about this, the radius, which is the center to center radius, is going to be r plus h. Now, so all I'm saying here is notice that we're going to use, if we have a problem on the test where I talk about altitude, you got to remember to add in the radius of the planet. And now this problem probably seems really silly, but it's not, okay? You should actually do the plots. So when I ask you to make plots, most people don't do it, but you should do this one and this one, okay? So, and I think you should do it in Excel. And because you've got plenty of time in lab this week, this would be a great time to make those plots. Finish up chapter 11 and make these plots, or just do these plots for fun. And this will help you in the Python as well, because you'll get used to dealing with prefixes, et cetera, et cetera. Now, I just want to point out something here. If you let G equal this funky thing, take a look. mg is the force due to gravity if this is G. And so what we see here is the magnitude of G changes with altitude. As you go up in altitude, you get less gravitational force. That means you have less gravitational field. More on fields in the next course. But this is pretty cool. And so if you plot this one, let's just go take a look at the plot. And I just want to show you what that looks like. Let's go over here. So here's a table. Here's the potential energy, right? And so you could see what these plots look like. And so this is maybe a little bit prettier. Whoops, that's kind of cutting off there, the H. But the idea is this is what the 1 over square law looks like. Looks like there's a little numerical artifact there from being at the end, but yeah. All right, and so here's what the potential energy looks like. And so notice as you go up in radius, I was alluding to this earlier, as you go to a higher radius, like if I go from 500 to or 5,000 to 10,000, my potential energy is less negative. So U final and U initial. Notice if you go up in the air, U final is greater than U initial. That says that delta U is positive, which is the same thing as our MGH formula. All right. And notice this is maybe hard to see here, but if I double the radius, look what happens here. Let's see. Let me see if I can get a good one. This one, I better check that formula there. I'm a little bit confused. This number looks like about 3, and this number looks like 1.5. That's not right. So I better check this plot myself and see if I screwed up. Think about it. If you double the, oh, wait, this is altitude. This is not, oh, I see. I just got myself. Oh, crazy Jorstad. Remember that altitude is not the same thing as radius. So when I double my altitude, I don't expect 1/4 of the force. So what I was thinking about was force is equal to GMM over R squared. If you double the radius, you expect the force to go down by a factor of 4. Again, if you double the radius, we expect force to go down by 4, but that's not the same thing as doubling the altitude. If you double the altitude, remember the radius is so huge that it's not going to change by that much. So if you double this number only, you have not doubled the radius. We have no reason to expect the force to cut in half or fourth or whatever. It's going to cut by some weird factor. So watch out for that. All right, I just got myself. That's always fun. All right, now I want to show you something here at the risk of boring you. When you're making these plots, here's a tip. Just because I give you the parameters in kilometers, there's no reason you can't change that to meters, right? So like this, I could just type in equals this number times 1,000, or I could type in times 1 E3, right? And then I could use a calculation. Let's say what were we calculating here? Let's say we were trying to calculate G, right? G in some units, we're going to say meters per second squared, right? And so that would equal big G, and then I hit the F4 button, times, let's see, what was it? By the mass of the planet, this one, F4, whatever it was. And I think, and then divided by the quantity, the radius, use this one, plus, I'm going to call it this here. Just give me a second. I know that's not right. But let's say this is H in meters, right? And so here, the mass of the planet was 5.97 E24. And so notice, if you put in 0, you get back 9.8. Looks good. And as you fill this down, whoops, that's not good. Let's say we do, let's say you go by 1000s, right? And let's get rid of these sig figs. We could see, and let's get rid of these sig figs. Oh, come on. I screwed up. This one needs a $sign, right? We could see that it changes very little when you even go up 1,000 meters, right? But if you start to go up, so that's why you notice maybe I did things like this. And here's a cool trick. Now, once I have the first 3 set, I just say it's equal to 10 times this number and fill it down. And you could very rapidly get all these things way out there. And notice I'm not doing any of the prefixes yet. Okay. And now what you do is you make a separate column with the prefixes taken care of. If you learn this trick now, it's going to save you some time. So this is equal to that divided by 1,000. All right. And this one, I guess we don't need to change. And so now you've got the height in kilometers, which looks pretty. So you can make your plot in terms of kilometers. You do all your math in scientific notation and whatever, and then you go back and you rewrite the answers by just doing a conversion after the fact. So I'm going to pause for a second and make sure that makes sense. Let me do this. Let me go back here. So again, notice you use scientific and you get rid of the prefixes, make an extra column in your data, and then do all the work in scientific notation or whatever you got to do. Then what you can do is you can just say, you can make your columns right here and you line them up. And now you plot these 2 columns. Got it? Take the time to do these plots and learn this skill. It may seem stupid, but why would you not do it? It's just, that's what matters to your career, is being able to be savvy with Excel and software. So do that. Okay. All right. And then let's look at 13.3 really quick, see if there's something else in there. I cannot emphasize enough, actually make these plots. Notice in 13.3, I do the same thing, but it's for a satellite. Here's a question before we go on. We got 5 minutes left. All right. What keeps the satellite up there? Again, we have a satellite orbiting. What keeps it up there? That's my question. I'm going to let you unmute and talk to me. Tell me what you think. What keeps the satellite up there? We know satellites orbit the planet. We know spaceships orbit the planet, space stations, all kinds of stuff. We know the moon orbits. The moon is a satellite, right? It's orbiting there. What keeps the moon up there?
Gravity.
It falls down. It's always falling down to Earth, but it's going so fast around that it's like it keeps on falling over the edge and going over, so it just keeps on going in a circle.
I would agree with that. And remember, gravity is the force that pulls it down to the Earth. Gravity is trying to make it crash. And so speed, you could argue that's a good answer as well. So all three of the answers that you guys brought up are all related. So yes, it's flying around and it's constantly falling. Think about this. If we ignore the Earth is going to cause well, even still, what force is acting on the moon as it orbits the Earth? Gravity, right? There's no air resistance in space. Now you could argue there's also gravity from the sun, but gravity is the only force acting on the object called the moon. So it's in free fall. It just never hits. It keeps missing the planet. So nothing keeps it up there. It's constantly falling and it just happens to never hit. So yeah, here's another thing. When astronauts are orbiting the Earth, are they weightless? I know, Joy, I'll get your question in a minute. What does it mean to be weightless? What is weight? Other than what an instructor does on Zoom while hoping his students reply via chat or unmute. mg, that's one. Okay, what's it mean in words, not equations? So weight is mg near the Earth's surface, but in general, what is weight?
The force of gravity on a mass.
The force of gravity on a mass. So, and that now near the planet Earth, we just saw this. Take a look. Near the planet Earth, we see this is the value of G for thousands of meters, right? Miles into the atmosphere. But once you get up, G starts going. Now, this is well above, this is 5,000 kilometers. This is a pretty high orbit. Most orbits around the planet are actually in the, I think, 400 kilometer range. So yeah, something like that. So satellites orbiting the Earth are usually about 400 kilometers, in the 200 to 500, maybe 1,000. Let's go back to that chat. Yeah. Okay. All right. So anyways, I've kind of got lost where I was going. It's distracting when I'm at, so it's not your fault. I told you to ask questions in chat, but now I'm lost what I was asking. Let me get to the point here. What was the question I was talking about? Does anybody remember? Crap. I'm tired. All right. Nothing keeps it up there. Weight is the force due to gravity. Is there gravity on astronauts in space? Yes or no? Is there gravity acting on astronauts in space?
Yes.
Think. Yes. Do not overthink this. There is gravitational force. So are astronauts weightless? No. Weightlessness is an experience. Okay? Weightlessness is when you feel like you're not having weight act on you. I can make you weightless. I can have, you want the weightless experience? I'll give it to you right now. Oh, I'm putting down the headphones. I feel weightless. I feel weightless. That's it. Now that is the worst demo ever. But anytime you jump in the air, you can experience weightlessness. You still have gravity acting on you, but if it's the only force acting on you, you feel like you're falling. So that's free fall. So yeah, if somebody drops you out of a plane, you feel weightless until the atmospheric drag picks up. Or if you're in an elevator and somebody cuts the cable and there's no emergency brake, then you would feel weightless. Turns out it's really expensive to send satellites into orbit and test them. So, yep. So there you're not free fall because you could tell by the lips, Ryan, right? So there you're not in free fall, but for the first second, you definitely had that feeling of weightlessness, right? You probably wanted to puke. But yeah, they actually have what's called a drop tower in a NASA research station where they have basically an elevator shaft that gives you 4 seconds of free fall. And that allows them to test stuff without having to send it up in the vomit comet. And a weird thing, just kind of a personal story. One time when I first started at Hancock, it was like my first or second year, 15 years ago or something like that. And there was a weird grant that Alan Hancock had for doing, they were trying to get training for students or they wanted to train workers for space. I don't know. And there were 8 people involved on the grant. And then they said, hey, we'll take one person from Hancock and fly them on the vomit comet. And they asked every single person at Hancock except for me, and nobody could go. And so then, because nobody else could go, they're like, well, nobody can go. You're not on the grant. You want to? I got to go on the vomit comet. It was super cool. So Hancock, start here, go puke in a plane. All right. I'm going to call that good I'm going to stop the live stream with that. Yeah.